Hello, welcome to gradient descent. So gradient descent is an optimization algorithm that iteratively adjusts parameters in the direction that reduces a loss function the fastest. It's the foundational method used in machine learning to teach models by gradually minimizing their errors. So here's an overview of what I'm going to be talking about. First, gradient descent uses. Second, we're going to be applying gradient descent to regression. A little bit of a review of backpropagation. Gradient descent analogy using a hill. Finally, gradient descent with the regression, and then coding gradient descent. So here's some machine learning algorithms using gradient descent. We've got neural networks, linear regression, and finally, logistic regression. So how would we set up the linear regression problem? So first, we're going to have the data, x1, y1, x2, y2, xn, yn. And then the model, which we have y hat is equal to wxi plus b. W is equal to the slope, B is the bias or the intercept, and X is the data point. Now we're looking at the errors individually through a graph. We've got data here. We've got a line, right? That's the W, right? The slope of a line. I mean, this is Y hat. I apologize. And we could see that the distance from the data point to the line is the error, right? So that's an individual error. Y minus Y hat, Y being the data point. So we'll define the loss function, which is denoted by W and B. So this is the mean squared error. For those familiar with regression, you should be familiar with it. It's Y hat minus YI squared. And then we're taking the summation. So we see the graph on the left. It's all of that added up, right? The difference between the data point and Y hat. So we sum that and then we divide it by n, which is the number of data points. So we see that that's the summation that I was just talking about. Now we've got 1 over n wx plus b, right? That's the y hat minus yi, right? And that's y hat. And that's the objective. The objective is to find values of w and b that minimize the loss. So let's come close to yi, where it equals to 0. So computing the gradients with backpropagation, we saw this earlier. We've got y hat equals xw plus b. The weights and biases, theta is equal to wb. That's the parameter space that we're interested in. I'm going to computational graph using the forward pass so we could see that we're trying to get to the loss basically. Y hat is a function of x and theta, theta being w and b. And the loss is y hat and y, the difference. So now we're going to use the chain rule implementation for the backward pass. And we could see that basically we're just backtracking from the loss all the way back to x to get to WB, right? So we saw this earlier in backpropagation computational graphs, the video that I created. And those are the two implementation, the two derivatives, right? The loss with respect to W and then the loss with respect to B. We see 2 times y hat minus y times x for the W, and then for B, it's 2 times y hat minus y. And we're gonna see this and implement this in Python in a simple example later on. But before I talk about basically gradients, let's give a physical example. Like how can we apply this to an example in real life? So say we're in some hilly valley area, right? We could see kind of as a hiker, right? So we could see that there's like a steep size and gradient, a step size and a gradient to how we could move. Okay, the objective being to be at the center of this little hill, which is basically a flat surface. So we could see that we could take this steep dive down, right? And the steep slope is a large gradient with large changes in the function. Larger steps are needed. Now, if we're in a flatter surface, a smaller gradient with small changes in the function, smaller step sizes are needed. And then finally, we get to the bottom, okay? And then this is completely flat. There's zero change, right? The gradient zero, goal is achieved. We've achieved the minimum, okay? The bottom of the hill. Now we could make a mistake and take way too large steps, right? And then we'd end up here. Step size is too large, so it basically overshoots. So here's something that formalizes it in actually like a, uh, a mathematical type curve, right? We've got a slope of loss at W1 is negative W1. We're trying to meet the minimum, W min, and one step of gradient descent. So the first step in iteratively finding the minimum of this loss function by moving W in the reverse direction from the slope of the function. Since the slope is negative, we need to move W in a positive direction to the right, okay? And then here the subscripts are used for learning steps. W1 means the initial value, which is 0, and W2 is the value of the second step, and so on. Another point to make is that when you need to start with initial values, right? Somewhere where you're starting off point. And then as the algorithm progresses, you're going to reach some optimal value, right? But you could always guess a starting point that's closer to the goal or farther away, okay? So let's go over again the regression gradient descent. We initialize WB, we calculate y hat, we calculate the loss. We've got x1, y1, x2, y2, xn, yn. That's the data points. And then we calculate batch gradient descent, and that uses all the data to compute the gradients. That's all the data that we have. We'll see later on in stochastic gradient descent that this is not the case, that they use samples. But in our example, in this vanilla gradient descent example, we're using all of the data. And we got the derivative of W with respect to L, the derivative of B with respect to L. And these update parameters and repeat until convergence, okay? So the learning rate, eta, is a small number. Remember when we saw that hill example that we need to take, the right amount of steps, right? If we take too large of steps, we could overshoot. If we take too small of a step, then maybe it'll take longer for us to get to the bottom of the hill. So we see this relationship here, W minus eta, and the derivative of W with respect to L, right? The gradient. And then same for the bias. And then convergence is achieved when W nu, which is the term on the left, minus W, the term on the W on the right, is less than some tolerance level, okay? And that's another thing that you could basically set, okay? That um, you could put in. Here's a loss minimization problem. The loss starts at 100. We've got some data here, right? And the loss starting at 100, I'm giving like as an example, right? Um, this line here, you know, it's pretty far away from the data points. It's at 100. It's pretty bad, right? We end up here, it's still pretty bad. And these are iterations that say, you know, gradient descent will perform until it finds the optimal value. And this would be, I mean, this straight line here would fit the data probably the best, right, in this example. And it ends at 50. I mean, this is just made up, but I'm trying to make the point that we go through iterations to find the optimal values of Wx plus b, right? Wx is the slope, W is the slope, B is the intercept. Now here's a gradient descent Python example. And this is going to wrap up what we've been talking about. So we got some data points here, x, y. We initialize parameters, w is equal to 0, b is equal to 0. The learning rate, 0.01, max iterations, 10,000. And the tolerance is like 0.00 to the 6 decimal places, 1, right? Something very small, okay? So we want that w and that new w to be really close. So here's the code. You could see that it's basically a loop, okay? And then we've got the wx plus b. The error is y predicted minus y, right? Y predicted meaning y hat. The loss is np mean, the error squared. Remember the MSE for the regression. And then the gradients are 2 times length of x times np dot error x. That's for dw. We saw that earlier. And then db is 2 divided by length of x times np sum of error. And we saw that earlier as well in mathematical form. And then we update the parameters. W minus learning rate times dw is equal to w nu. Okay, and then the delta, same for b, right? And then the delta w is the difference between w nu and w. And then we see that the delta, if delta w is less than the tolerance and delta b is less than the tolerance, then it converges and it breaks. Okay, the loop stops. So when we look at the output, we could see that as it goes through the iterations, and I made it by 100, the printout by 100. We could see that it eventually converges, okay, to this 1.99 and this 0.03, 0.003, okay, and that would be our final loss. So that's kind of how it works. Gradient descent would work from a programming perspective. Thanks for tuning in, and hope to see you soon.